So good afternoon, everyone. We're really lucky to have Chad Kruger with us this afternoon, and he's going to talk with us about carbon sequestration and soils and carbon farming and all of those types of things. I know that's been in the news a lot. There's been a lot of articles about it, a lot of research papers about it, terms like carbon farming and regenerative ag and all of these types of things. So we're really lucky to have Chad presenting some good information on this afternoon. And Chad is the director of the Center for Sustainable Agriculture and Natural Resources. He completed an MS in 2003 in land resources from the Gaylord Nelson Institute for Environmental Studies at the University of Wisconsin-Madison. He has served on the 2007-2008 Washington State Climate Action Team, co-chairing the agriculture sector carbon market workshop, the 2010 Washington State Climate Change Working Lands Technical Advisory Group, the Washington State Energy Strategy Technical Experts Panel, the Northwest Regional Biocarbon Initiative, is a member of the Washington Department of Natural Resource Expert Council on Climate Change, and was a commissioner on the Douglas County Water Conservancy Board. He is currently a board member for the Northwest Ag Business Center, the advisory board on the advisory board of the Northwest Environmental Forum, the WSDA Dairy Nutrient Advisory Committee, and the WDNR Climate Resilience Advisory Panel. He was raised in Washington State and has family roots in agriculture, both in Eastern Washington with wheat and cattle farming near Spokane, and in Western Washington with berry farming near Whatcom County. So what a plethora of experience and expertise that he has, and we're really lucky to have him here with us today. So thank you, Chad.
All right, thank you. And let me know if you can see the screen on the presentation, just to be sure.
Yep, I can see it.
Okay, great, thank you. Yeah, so when you hear that, the bios on yourself, you forget all the things that you've done. But in reality, for the past 5 years, I've been playing at university administrator and don't get to do a lot of fun stuff anymore. And when the request was originally brought to do this, in fact, the right person to do it would have been Georgine Yorgi, who works with me, because she's been the one for the last few years kind of the most tuned into all the issues and up to speed. And yet when this was going to be an in-person event, we were looking at travel schedules and it was going to be difficult for her to go. So we decided to send me. Well, and now we don't have to travel. So we probably should have had her do it, but I want to give her a lot of credit for the content you're going to see and the organization of it and the thinking behind it, because she really is the brains. And the next thing I'm going to point to is that we have forthcoming an extension publication specifically on this question of carbon sequestration potential in cropland soils in the inland Northwest, knowledge and gaps. And right now you can actually access essentially a pre-review version of that on the WSU website. That's the link right there, and if anybody wants it. And I also want to credit Karen Hills and Sonia Hall for a lot of work on this particular document, really working through all the information, getting up to speed. And Claudio Stockel, who his name will pop up a few times in the context of what we present. He's collaborator for probably 17 years now working on this with us and does a lot of work on modeling on carbon. So a lot of what I'll cover is in this document. Some of it's not captured in this document, but this is a pretty important resource. There's another resource that if you haven't seen, there's still a few physical copies left of the book that we produced on basically the inland Northwest grain production systems. It's kind of a state of the science of what we know about these systems and management questions. And there's a lot of work on soils in that. About over half the book is actually soils related. Okay, so I'm going to get right into this, and I'm going to cover some territory today and probably leave you with a lot more questions than I provide answers, but I think you'll get at least a pretty good picture of what we know and what we don't know, and then why it might actually matter. So why do we focus on soil carbon? It's an important indicator is basically the bottom line. It's an indicator of a lot of good things from a production standpoint, from an environmental standpoint, and therefore it tends to get a lot of the attention when it's not necessarily that soil carbon itself is the objective that we're going for, but it's the most, probably the easiest indicator to actually try and measure for a lot of different reasons. And why do we really care? Because for a long time, agriculture in all of our traditional forms and even some of our more modern forms has really done a number in a negative way on soil carbon. And so this particular data set is off of the Cook farm near Pullman, and basically shows for a number of different soil types, once we went from native ecosystem to some kind of cultivated ecosystem, you can see we dramatically reduced the amount of soil organic carbon that was in these soils that was there. You know, so depending on, and in the Palouse, a lot of this is slope and orientation driven, basically where the carbon erodes off the fields. But you can see anywhere from 26 to 73% of the native soil carbon or soil organic carbon has been eroded from the fields. The story is different when we irrigate, and particularly when we irrigate in places like central Washington that historically are very low carbon soils. So whether they're, you know, Quincy sands or other types of soils in like the Columbia Basin and a lot of river valleys, these are, you know, historically geologically low carbon soils. And when we come in and we add water and we add fertilizer, we actually grow a lot of biomass. And so what you see happen is when you start to cultivate in some of these systems, all that addition of external inputs actually leads to an increase in soil organic carbon over native sites. So the story isn't always that we've lost. And in our region and our state in particular, there are many situations where we actually already gain significant amounts of soil carbon. But it's this important thing that we'll get to on what are actually driving the dynamics from an ecology perspective and how that works. So let's look at those dynamics, kind of talk through them and get a real sense of what the issue is. Georgine had this great vision that when we were working on this a long time ago to think about the problem of soil carbon dynamics as a bathtub. And essentially what we're doing is there's various different drivers that will add carbon to the bathtub, and there are other drivers that will pull carbon out of the bathtub. Some of those drivers are biogeochemical, so they're natural systems, and some of those are management related. And so, you know, what happens to that carbon? You know, it comes into the system through plant material primarily. You know, we take carbon dioxide out of the atmosphere through plants, and we fix that as sugars or carbohydrates in plant material, and then when those decay, they become soil organic carbon. We lose that carbon through erosion and distribution across the landscape, and also through oxidation, excuse me, where that carbon just goes back straight up to the atmosphere. And in some cases, we leach it out through different forms into our aquatic systems, which also put it back up in the atmosphere. There is a little bit of deposition of carbon, usually because it's coming from someplace else and landing in your fields. That's usually more of an issue with nitrogen. But when you take the sum total of it, you're basically adding up, you know, simple math. Are we getting in as much as we're losing? Are we getting in less than we're losing? Or are we getting in more than we're losing? And for the last 150 years in our region, largely we've been losing out of the bathtub, though we're starting to see some important corners being turned on that. Okay, so what are the things that we can actually do from a management perspective to affect that soil carbon pool? To increase the carbon input side, we can keep plants growing throughout the year. We can use cover crops. We can double crop. We can eliminate fallow when it's possible. And you'll come back and I'll show you some information later on that says this may be the single most important thing we can do on a lot of the landscape we have is actually reduce the fallow periods. And then when feasible, adding perennial crops such as a grass or something like that into a rotation, increasing the crop residues that are left behind, and then adding amendments like manures, biosolids, biochar. These are the kinds of how do you increase the amount of flow into the bathtub. And then on the reducing the loss side, we want to reduce disturbance. And if you look at a lot of the literature and historical work and a lot of the historical activity related to carbon, this is the key, reducing the disturbance by reducing tillage, presumably that reduces erosion and the carbon loss through erosion and also, potentially reducing burning and residue management. But a lot of our activity has actually been focused on this point because the primary orientation of how we've been concerned about managing soils really has come from an erosion perspective, particularly in our region. And I think we've maybe misunderstood or misattributed the carbon sequestration question to the erosion question. The erosion question is a super critical question, but I think sometimes we've assumed or made leaps in our assumptions about how important tillage is to carbon dynamics, and we're starting to see that it's not quite as simple as we first thought. And we'll get into that. Okay, so how can, what affects that soil or organic carbon pool or the bathtub? And there are a couple of key things here that we really can't manage, and then a few things that we can manage. And so the potential for organic carbon is really set by geology. So what is the soil type? What's its depth? What's bulk density? What's the source material for those soils? That really has a lot of the factors in terms of what the ultimate kind of, perfect picture, what's the potential for organic carbon in a system. Then we come to the more moderating effects that come really from the climate in terms of what's actually attainable. And so rainfall is a huge one. And in our case, for the most part, rainfall is our limiting factor in terms of attainable organic carbon in soils throughout much of the Northwest. It's not always the most, and on the west side, clearly rainfall tends to be less of an issue, but it's still an issue in terms of timing of that rainfall. Temperature, if it's not cool or if it's too cool, it's hard to get enough biomass to grow, but also the hotter it gets, the faster that you actually turn that carbon over and lose it, and of course solar radiation, which affects plant growth. The actual organic carbon really comes down to management. So once you've kind of set the geology and the climate, then you have the question of what can we actually do in terms of our manipulation. And three key things: plant productivity, our rotations, and then the management of the soil system itself. Okay, so this is a complex issue, and there's a lot of factors that come into play that are not necessarily obvious at first strike. And so we're going to talk about a few of those that affect this question of, are we increasing or decreasing soil organic carbon on any particular site based on management? And the very first thing you need to know is, where are you starting? So what's your soil organic carbon when you start, so that when you think about applying management, you can have some assessment or projection of where you could possibly get to with your management strategy. And we know that soil organic carbon varies significantly by location. And so what you're seeing in this image, this came from the REACH project, which was really an inland Northwest grains focused project. And you can, in the cutout there, you can see kind of where that weird shaped map actually comes from. But this is, Idaho, a little bit of northern Oregon, and mostly Washington, pretty much the east side of the state, where the blue is the annual cropping zone, the yellow is what we think of as the intermediate cropping zone, The brown is where we think of the summer fallow, and then the irrigated is the green. And what we know is the further east you go, the more soil organic carbon that you have native to the soils. And that's just, it's a climate and soils factor, not so much a management factor. Wetter in Moscow than it is in Lind or in Prosser. The kind of the unusual change of climate or unusual influence on climate, of course, is the irrigated region, where we have supplemented rainfall with either surface or groundwaters, and actually have had a fairly significant effect on soil carbon, as I showed you a few slides ago. But generally speaking, the further east you are in our region, the higher your native soil organic carbon is going to be. So where you start is going to be higher. Then we go to the question that soil organic carbon is not a static thing. It changes over time, and it changes both by management as well as because climate is variable. And so you see changes over time that are really a reflection of variable climate, and you see changes over time that are a reflection of management. And what you see in this particular slide is, and I can't actually remember where the data is from, but it's the general concept of the bottom line there. The lines are models, the dots are actual measurements of carbon in a long-term scenario where you have basically an unmanaged cultivated system. The NPK-Mg is kind of conventional fertility system, and then that top one is where we've got manure added to the system. And then you see that variability right in the middle, where there's kind of the sawtooth action, has a lot to do with the fact that there were fallow years included in this system. And so what you can see from this is, even in an unmanaged system or a conventional system, it's not always the same where the soil organic carbon is. It does change. And the last one, and I think this is a really important one to wrap your mind around, is where you start on any given site affects your ability to influence soil organic carbon levels. And what we're showing here is we're showing two sites that are separated from each other. One is Heppner and one is Colfax. And basically, we've got the same management system applied. It's a no-till management system at two locations. And yet both of these systems, according to this graphic, are actually losing carbon over time, even in a no-till management system. And you see the slope of change is different. So the change in the Colfax site, which started with a lot more initial soil organic matter, actually loses soil carbon faster in this particular production scenario. Now, we've got other production scenarios that we've looked at that kind of can change whether you're losing or the pace at which you're losing. But it's really important just to understand that if you start with a lot of carbon, it takes a lot of investment of carbon, of additional carbon, to stay there if you're doing any kind of production on that system. And if you start with less carbon, a little bit of work goes a long ways. And we've even looked at this question of taking the same site, so the same field, and looking at different production systems and production scenarios, and using NRCS provides a range of soil organic carbon levels for any given soil. And if you start with the low end of that range versus the high end of that range, you would project in some cases to increase carbon, in some cases to decrease carbon on the same field with the same management strategies. So the bottom line of this complexity is you really need to know where you're starting in order to understand how the management that you apply actually will affect your outcome for soil organic carbon. Okay, so with that, I'm going to shift now to talking about some of the regional work that we've got, and we've got some places where we've got really good data sets, and we've got other places where we got really big gaps. And so I'll talk through what we know at this point in time, and then I'll talk through a little bit of what our hopes and dreams are for being able to fill in some of those gaps. Okay, so the very first chart I'm showing here is a paper by Dave Brown and Tabitha Huggins, or excuse me, Tabitha Huggins and Dave Brown, where they looked at all of the soil carbon data sets that they could get their hands on in the grain production region in the inland Northwest. And I can't remember the number, but this included both published and unpublished studies, and in some cases, studies that were still sitting in file cabinets. And what they did is they took all of those studies and they tried to figure out, could we replicate the sampling strategy that was employed in this study, and actually, is there enough information to think that we could go out and replicate the exact sampling that they did? And if they couldn't replicate it, they eliminated those studies from consideration because they didn't know what might or might not have been included in terms of the nuance of the samples. Then they got it down to where they knew they could replicate the study. They broke those up by what they called agroclimatic zones, which is similar to that map I showed you earlier. And actually this was done before that map was produced, but they broke them up. They broke them up kind of by management system, and then took each of the individual sets of studies and tried to see if we were to look at this and apply a fairly simple statistical tool of cumulative probability, what could we say about the potential soil organic change or the actual soil organic change on any of these given systems in any of these given zones? So let's just take the top one, the no-till management agroclimatic zone 2, which is the annual cropping system. So think Pullman. There were 12 studies that they found that they could actually replicate exactly what the sampling was. The average number of years of those studies was 14. And then what was the reported change of soil organic carbon? And what you see here is that the average reported change was 0.71 milligrams of carbon per hectare per year. But when you applied this statistical tool of the 20th, 25th, 50th, and 75th percentile, what you see is you get a really, really wide range of studies even in that one zone with no-till management in terms of what they're showing has happened. And so how do you know which one's right? If you're thinking about, you're trying to make decisions about how much carbon can you get in, say, the annual cropping system of the Northwest, do you pick 0.71 megagrams of carbon per hectare per year as your expected amount? Do you pick 0.64, or do you pick the really good one of 1.04? Or are you really risk averse and say, well, we can only guarantee, around 0.21 megagrams of carbon per hectare per year? And I think what they showed here is there is a lot of variability in the data sets that we do have, the actual physical data sets that we do have, and there needs to be a lot of discretion applied to forecasting or projection that if we apply certain management regimes or technologies, what do we think we're actually going to get? And so, I think I'd encourage everybody to go read that paper, because this was the first attempt to really kind of comprehensively build a picture of what we know from experimental work and sampling in the inland region. So then I'm going to go to the next study, and this study was actually done at the same time by the same group of people. This one is led by Claudio instead of Dave Huggins. But what we were looking at here is, instead of looking at the experimental data sets, we were building a modeling tool where we could try to forecast what might happen given a lot of different variables across this region. So we were kind of taking that same set of agroecological zones, the same set of types of production systems and management systems we were looking at, and trying to figure out, what do we think is projectable? And so what you have here is kind of, this is blocked into two pieces, lower and upper boundary, and the lower and upper boundary really refers to that range of potential impacts depending on where you started with your soil organic carbon on a given site. So if you started low in terms of the native, or the range that's presented in the native, or if you started high, you're likely to have more or less effect. Then we looked at the question of, how long are we going to be managing and trying to measure that soil organic carbon, because we know it's going to change over time. And so we took two different kind of periods of samples. The black bars are 12-year study, and the gray bars are 30-year studies. And so what you see, generally speaking, in this data set is the rate of change per year is lower in the 30-year frame than the 12-year frame. It's not always lower, but generally speaking, if you have a longer period of time, you have to assume the management strategy that you're applying is going to have less of a benefit on an annual basis. And then the other thing we looked at is the brown is winter wheat, summer fallow, the yellow is intermediate, the blue is annual cropping system. And so we use Lynn, St. John, and Pullman as our sites in that. And in the Pullman system, obviously, because of the higher rainfall, we have more options. So we included a barley-based system with reduced till and no-till, and we used a pea-based system, or a system that includes barley and a system that includes peas as rotational crops. And what you see here is kind of an interesting thing in that obviously the annual cropping systems have a lot more potential for carbon sequestration than the drier systems. But the reduced tillage system in the annual cropping system actually isn't working very well from a carbon sequestration potential. I think that's another really important finding. So, a lot to look at here. But the big picture I want to kind of point you to is over on the left, the megagrams of carbon per hectare per year. Most of these results are coming in that, somewhere between 0.2 to 0.6 megagrams of carbon per hectare per year. And I'm going to back us up just for a minute and look at the Huggins and Brown study again. And guess what? Our modeling tools are doing a pretty good job of forecasting what we see in the actual data sets. Okay, so, and we see in terms of, we're probably looking in the 35th to 40th percentile, so not necessarily the 50th percentile, certainly not the mean of the existing data sets, but most likely in that 30th to 40th percentile of kind of the existing data set. So that tells you that if you're going to forecast what our potential for soil carbon sequestration is in the region and the dryland production systems, you need to be pretty conservative based on the data sets that tend to get put out there and celebrated. And let me just say one more thing about that. There's a lot of people that have put out some pretty incredible numbers in terms of soil carbon sequestration, and you see a lot of these passed around, and some of them are actually, quite frankly, impossible to believe. And so I think what we see happening is a little bit of cherry picking data that looks really phenomenal, and we see cherry picking for a couple of different reasons. I think a lot of times the reason that particular soil carbon data set was pulled wasn't necessarily to create a representative sample that could be replicated, as much as it was to look at a really unique phenomenon that somebody had noticed, or to look at a production system that was really on the cutting and bleeding edge in terms of what's possible, but may not be something that's quite replicable across the system. That doesn't mean that there aren't, real values in some of those data sets. I think it just means that we need to be a little bit more conservative in terms of our assumptions about what can be done if we're planning to try and implement management practices across the landscape, across all different kinds of producers, all different kinds of climates and soils, and trying to get somewhere positive. We just need to be a little bit more conservative. So the next thing I want to kind of point out, and this is basically the same group again. This one's Osama Zaire is the lead author, where we took the work that I just showed you from Claudio and said, soil carbon isn't the only factor as it relates to the whole greenhouse gas footprint or carbon footprint. And essentially we put the nitrous oxide emissions and the fertilizer and fuel consumption emissions of these systems together to try and kind of come out with, what's the net emissions from these production systems, kind of a life cycle footprint. And what you see here is the gray bars below the line are obviously the soil carbon sequestration potential. But when you look at some of the other factors, the nitrous oxide one in particular is a huge source of greenhouse gas footprints. And in a lot of the systems that are, pretty good about sequestering carbon, they're also pretty leaky from a nitrous oxide perspective. And they just flat out use a lot more nitrogen. So when it comes right down to it, your net emissions may actually be quite a bit higher in some of the systems that are better from a soil carbon sequestration potential than others. But you've got a couple of them that are looking pretty good. So that high rainfall cereal grain production system and no-till ends up with a pretty low total net emission footprint. And that's a positive thing. Okay, I want to shift now to talk about the residue management side of the equation, because what we're gonna come out to a conclusion, I'll just kind of give it to you up front, is what goes into the system is actually probably by far the most important factor in terms of determining your the level of the bathtub, if you will. And so this particular work was done by Stephen Machado, looking at the Pendleton long-term site, which is the longest actively managed long-term research, agroecological research site in the region. We're getting on almost 100 years of management there. It's gone through a bunch of iterations, but anytime that we want to actually go back and kind of tune a modeling tool or a forecasting tool, or really understand the long-term dynamics, we basically have to go to the Pendleton data set. And Stephen right now is kind of the curator of that data set, and he's managing the site. And so what you've got here is basically an unfertilized treatment, a low traditional or conventional fertility treatment, a high conventional fertility treatment, a treatment where pea vines were added into the system. So basically an additional crop residue that also brings some nitrogen, extra nitrogen with it. And then a system where manure was added to it. And then a system where burning is done and there's no nitrogen added. And what you see here is kind of what you'd expect to see. When you burn it and you don't add any nitrogen back, you get the worst possible scenario, burning all your residue. When you don't add any nitrogen at all, you're not producing very much, and therefore you're not going to put a whole lot of soil carbon in the ground. But when you get into the place where you're starting to put some fertility down, you start to mitigate some of that long-term soil carbon loss because you're increasing the amount of biomass produced on that ground. And then of course, when you come in and you supplementally add a crop residue, a pea vines, you're starting to really make a dent. But then the big one, when you add manure, you definitely start to make an impact on your soil organic carbon. And in the case of the long-term treatments at Pendleton, what you essentially see is that's the one system that really has kind of been sustainable over time in terms of its soil organic carbon level. So looking at some other things, there's another really interesting site that's now almost 30 years in management, not quite 30 years, I guess that's probably only about 20 years, but for a long time, this GP17 site in Douglas County, North Douglas County, has been getting biosolids applications to it. And so what you see here is the red is basically no nutrient application at all. The blue is kind of a conventional fertilizer application. And then you've got 3 rates of biosolids added per acre. So 2 dry tons, 3 dry tons, 4.5 dry tons. And what you see here is in particular in that 4.5 dry tons, we pretty much doubled the carbon in that soil. And the more you add, the more it's increased in the soil organic carbon. So I put a couple of things together for you to look at here. So the red bars come from that Stockel study, or the Claudio Stockel study that I showed you the Lind and Pullman sites. So I just put a couple of those data points. So that really, really, really good system, the no-till system, upper end of the bounds in Pullman, and kind of the worst case scenario reduced tillage system in Lind are the ones that are circled there. That GP17 site, I've got the data sets from the control, which was basically nothing added, and then those 3 different rates of biosolids application. And what this does is it kind of shows you on an equivalent basis of the same amount of time, roughly, how much more significant the potential increase of soil organic carbon is above and beyond kind of traditional cropping systems based approaches. When you bring in the material from outside, you can make a huge difference. Of course, there are questions and limitations about how often we can actually bring in that carbon from outside from an economic perspective. Okay, so kind of wrapping up this, what do we have in terms of the data in the system? This chart was put together as though everything hit in all these different changes hit in 1931, when in fact they didn't. They started at different points. But it kind of says, okay, what if we would made all these changes at the same time? And again, this is off the Pendleton site. What might actually matter the most based on what we know now in terms of the production approaches that we could do? And so we know prior to making any of these interventions, it was basically a wheat fallow plowed system, going the wrong direction on soil carbon. We keep doing that, we're going to keep going the wrong direction, just maybe not quite at the same steep dive. We shift from a plow to a less inversion tillage type of approach. We're oxidizing a little bit less of those residues. We make a little bit of a difference. We make a much bigger difference when we decide we're not going to fallow anymore and we're actually going to start producing continuous wheat, even if our wheat yields aren't as high as they would be if they fallow. I think that's an important message, but we're still plowing. Once we go to continuous wheat with no-till, even if we're not getting as much total yield on the wheat, that's when we really start to see a major positive effect on soil carbon. And basically what it is we're getting a lot more residue put into that system. And then of course, when we go to grass pasture, which pretty much takes all of the tillage out of the equation and has, a green growing crop more of the year than even wheat, kind of more of the space filled in, if you will, that's obviously the best scenario. Okay, so conclusions from this piece, and I'm running a little slower than I thought I would be. Tillage is one important factor. It's critical to erosion, but it's not necessarily the most important factor in terms of soil organic carbon. And in fact, what we know from tillage is sometimes we're not losing that carbon from the field at all. We're just moving it around in the field, or we're washing it down the rivers, and it may be sequestered in the ocean or in the river system rather than where we want it. But cropping intensity and carbon inputs matter a lot. And so for maintaining soil organic carbon in dryland winter wheat summer fallow systems, you're going to have hard time doing that if you're fallowing. And if you have the potential to pull fallow out of that system, you're going to do the most for soil organic carbon. However, I want to point out that may not or should not necessarily be your decision factor. That's just, if you're trying to increase your soil organic carbon, it's pretty hard to do it when you're fallowing the ground for, 15 months out of every 2 years. And then when we really think about it on an area level, obviously our opportunities to build soil organic carbon are best in the higher intensity irrigated systems, the annual dryland cropping systems, or where we can add those organic residues, whether they're, manures, biosolids, some other kind of residue that gets into that system. Potentially, if you can get a cover crop in that system, that helps reduce the fallow in the system. Those are the real things that we've learned to date. So I'll wrap this session up that, by and large, the closer you are to Pullman, the more we know about soil organic carbon. And I wonder why. We've done a lot of work out at Lind over the years on this, but we just don't have kind of the depth of knowledge once you get outside of the dryland system. There's been some work done at the Puyallup station on organic production systems and soil carbon. We're starting a lot of work in the Mount Vernon Center, focused primarily on the annual cropping systems of Western Washington. There's been some work at Prosser and Othello. Hal Collins did a lot of that work looking at just what's the effect of irrigation, as well as can we actually do anything from a management perspective. But the idea behind the Soil Health Initiative was to really get a distributed sense across the state of experimentally what can we do to push these systems, and also where are we at. And so Deirdre Griffin-LaHue is actually in the process working with WSDA to try and update the statewide data set, kind of baseline data set. She's got a lot of work going on in the irrigated central part of the state where we have very little. And she's also doing some similar work up in Western Washington in potato production systems, just to try and get us a much better sense of where are we actually at right now with that initial soil organic carbon and initial soil health overall, comparing some, call them best and worst case scenarios, largely from producers' fields. And then the idea is, can we correlate the producer experience with some of the experimental work that's going on and being initiated all across the state? Okay, so the last thing I'm going to leave you with before we get a few questions in is, why do we want to focus on carbon, and does a producer really care about carbon? And I'm going to talk about a few individuals. And I think the key here is we've tended to fixate on carbon for a number of reasons. Like I said early on, because it's an easy indicator to say a lot of things that matter, but it's not necessarily why somebody would do it. And so we've got a series of case studies that we've done that are largely Eastern Washington focused, but there's a few that are not specifically Eastern Washington or Idaho or Oregon. But great case studies you can go look at that deal with a lot of issues, some of which are related to carbon, some of which are related to climate and nitrogen. But they're really valuable resources. And then I'll talk about a few. So this was an interesting study from the Cook Farm in Pullman, where the system has been put into a long-term no-till system, really tried to be an advanced production system. I'm not sure that it's one that any producer would necessarily replicate. It was really designed to answer questions. But we know that in that field, you have a really high degree of variability across the field of carbon, high variability of nitrogen, high variability of moisture content, high variability of yield. And we're trying to manage for that. But one of the things that was really interesting is leaving that standing stubble in a no-till system when compared to a clean-tilled field next door actually had a pretty serious effect in terms of what happened with moisture that fell from the sky in the wintertime. And so Dave Huggins got his crew out after a windstorm where the snow blew all over the field, and basically they went out and measured snow water equivalent or snow moisture equivalent, and then projected that back to what would the change in yield be with all that extra moisture that went into the soil where it fell rather than being blown off the field or blown down the field or somewhere else. And it's a pretty significant factor depending on where you're at in the field. So if you were able to keep that moisture in the ridgetop soils, where in a clean tilled field that snow would have been blown off the top of the field, that was worth 13 extra bushels per acre. In the valleys, it may only be 3 bushels per acre, but that's a pretty important factor in terms of profitability on that farm. So if you're a dryland farmer, the kinds of things we've been talking about doing from a management perspective that we think will benefit soil organic carbon, you may not actually care that much about the carbon, but those management effects or management strategies may actually be very important for helping your moisture management and potentially even yields. So another guy that gets a lot of press is Dale Geese. And Dale's been a long-time innovator on soil health, and I think some of you know him. He's the guy who pioneered the use of mustard green manures as a cover crop in potato production systems. And this is a very intensive system, a lot of tillage, and yet he's got some of the most interesting results of any kind of commercial farm in the state in terms of what he's done for soil carbon. And I'll see if I can play a couple things for you. So I think that's Nicole Emberson and Leslie Michael that you see out there going out to dig in the field. But what happened here is, 12,000 pounds of biomass to this mustard cover crop, basically flail chopped and then disked down into the soil. Obviously, they're doing it for a biofumigation purpose. But one of the interesting things that's happened is in the 15 years that Dale did this to start, and he's now going on about 25 years of doing it, he more than doubled his organic matter. And kind of an interesting factor is, that organic matter is probably good, but it's probably not that valuable from a carbon perspective. But what he found is it increased his water holding capacity by 30%. So when you get these really hot, dry days in the summer in the basin, the hot nights, the center pivots a lot of times can't keep up, and you get crop damage or crop loss on these high ET days. And if you hit it the wrong time in a potato production system, that can be really, really impactful. And so what Dale has found out is after he started doing this and was doing it for 15 years, even though his center pivots are no different than anybody else's center pivots, they just don't dry out at the pace that the others do. And so he gets good yields, high quality, and that kind of thing. And so here, the carbon itself has a value, but it may not be that important, whereas that impact on crop quality is super important. And this one is an interesting one from Northwest Washington, where we've been working with kind of a crazy berry grower. And what he's done is he's a raspberry grower who has just discovered that, after 40 some odd years of growing raspberries in the same field over and over and over again, his soils are really different. He's seen that same effect that I showed you on that Palouse set of soils very early on, of just a massive decline in the organic matter levels in his soils. And his concern was, it's having a lot of detrimental effects on his raspberry production system, and the berries just don't last as long. And that's probably attributed to a disease issue that comes from the fact that, if there's not enough good organic matter or fresh organic matter for the good microbes to be feeding on and turning over, well, the bad microbes that feed on a plant tend to get an advantage. And so he started doing this, where he started applying manure in the row to raspberries to try and sock some manure back into that system. We don't yet have kind of any long-term data sets on what he's done for his organic carbon, but he's telling us that anecdotally, he's seen an effect in his berry production systems. And we're just about to publish a couple papers that are trying to finally capture a little bit of what that effect might be. But, it's pretty clear that he's having a positive effect just by focusing on this question of adding materials that could add carbon. And again, I think like Dale's system, he's probably not going to be adding enough carbon for it to matter from kind of a carbon value perspective. But from the perspective of what it might mean for his cash crop, it could be very, very, very important. And then the last one I'll leave you with is Morris and Beth Robinette from the Lazy R. Morris kind of got excited about holistic management probably 30, 35 years ago, and has really changed the way they've managed their grazing system. And where his father used to do a lot of haying, they've basically gone to a very intensive grazing system, planned grazing system. And in this field that he's standing in there, he's actually tripled his organic matter. And you know, you don't have to go far and look at fence rows next to his neighbors and see that matters a lot, especially in July and August when these soils start to dry out in these production systems and everybody else's grazing ground is toast. Morris still has green growing grass to feed his cows. And so I think the bottom line I'm giving you here with these last set of individuals is, it may not matter to the producer so much what their soil carbon number is. It may not be that valuable from a big picture of what's the carbon cycle thing going on, but there are very likely some very real value propositions to producers of managing for carbon. So with that, I'll end and open it up for any questions that you have.
Well, thank you, Chad. That was a great presentation. I learned a lot, especially about all the complexity with with soil carbon and how it's gained and how it's lost. And I think from a climate perspective too, the point you made about all GHG emissions that are coming off of a site, not just carbon, but nitrous oxide and those types of things too, to be looking at, and different management techniques and how those impact all those different factors. So thank you, and I will turn it over to Jan, who is able to monitor the questions coming in.
Yeah, we have one question here from Eric. This was from a little bit ago. He was asking, what are the biosolids exactly? I don't know if you...
So the biosolids, the GP17 site, those biosolids come from the King County wastewater system. So they're human-based biosolids.
Okay, good. And we do have a few more minutes for questions. So if anyone has questions, feel free to either raise your hand and I can unmute you, or just type them into the question box and we can read them for you.
All right, everybody got all their questions answered.
Yeah, I'm not seeing anything else come into the question box here, so let's see.
I have one quick question, Chad. You mentioned early on, I think in the talk, about perennial systems or working perennials into the system. Is anyone experimenting with perennial grains or anything like that? Or is there any
Great question. Yeah, so, you know, if you think about the evolutionary development of plants, you know, not so much the woody species, but the herbaceous species, we've selected for annuals in most of our cropping systems because annuals yield way more. And essentially what that is the plant allocates more carbon and energy towards the fruit or the grain rather than towards the roots and shoots. And so if you're thinking from the perspective of carbon, the perfect plant from a carbon perspective is one that's allocating very little to its reproductive piece, which is usually what we eat, and allocating all of its energy and carbon back to roots and shoots. The challenge is that doesn't tend to be very economical except where you can graze it. And where you can graze it, it can be very economical. And there's a lot of really good examples of that. But if we're going to eat breads and potatoes and tomatoes and things like that, you know, we're really kind of stuck with annual crops, except for maybe the potential where you could come back and you could try and say, okay, let's select back for perennialism in a crop that actually has some yield potential. And so there has been some work. There's been some work at the Land Institute trying to pioneer perennial grains. Steve Jones's group at WSU has historically kind of gotten in and gotten out of the perennial grains. In fact, a couple years ago, one of his grad students actually published a paper naming a new species of wheat based on perennialism. And so it's always kind of been this sidebar. Right now, they actually have a fair bit of funding from a donor to try and push that a lot further. Dave Huggins, when I first came to WSU in 2004, we actually had some of Jones's perennial wheat or perennial grains in one of the experiments. The problems, you know, and what Dave was interested in is, could we capture this perennialism value from a carbon sequestration? The problem at the time is the perennial grains weren't very perennial. And so they just didn't work very well, and they needed a lot more work. And I think we're, depending on who you talk to, anywhere from 10 to 100 years before we've got that figured out.